Hello, welcome back to our next lesson. This lesson begins on page 18 in your notes. And for the next couple of pages, pages 18 and 19, what we're going to look at here is basically just a review of things that you've already done previously, perhaps in Math 1700 or some other courses, on calculating the slope of a straight line. And it's fairly straightforward. You know at least a couple of methods that you can use to calculate the slope of a straight line. And in fact, once you know the slope of a line, if you have a point that's already on the line, you can actually calculate the equation of that line. So we're going to be looking at a few examples here, a few select examples on page 18 and 19. But like I say, this is basically just a review of things you've already seen before. Here, for example, on the top of page 18, there's a nice line they've got graphed. I can clearly see coordinates of points that are on that line. It's sloping upward to the right, so we know the slope is going to be positive something, and it doesn't look like it's very steep. I suspect that the slope of that line is less than 1. So we're going to calculate the slope. Now, you know a couple of ways to do this. One way would be to locate 2 points that are directly on the line whose coordinates you can very easily see. You have to make sure you pick appropriate points. So let's suppose I picked this point right here. Now I can see that that's actually the y-intercept, isn't it? The y-intercept is 1. So the coordinates of that point would actually be 0 and 1. I could even write that here. And so now we want to pick another point that's on that line. And as long as the line is passing through the grid mark so you can see exactly what the coordinates are and calculate rise and run, well, then that would be fine. Here, this is a good point right there. Now the coordinates of that point is 2, 2, 2 and 2. Here's another point up here. The coordinates of that point, for example, would be 4 and 3. Now, one way to calculate the slope, probably the most basic way, and the way you probably did it at first when you first learned about slope, would be to just make a triangle right here, a right triangle. And what we're going to do is actually look at the rise and look at the run. So take your pencil, put it on this point here, say starting off, and let's suppose we make a movement to the right. Now remember, direction is important for slope if you're going to use this method. A movement to the right or upward, well, that's considered a positive direction. But if you move to the left or downward, that's considered a negative direction. So if you're going to use this technique, direction is important. So I put my pencil here and I just count how far I actually move to the right. Well, there's 1, 2, 3, 4. Horizontal movement, of course, is what we call the run. So in this case, my run is positive 4. And then if I go upward, I have to go up to the second point that I picked, you see? So I would go up 1, 2 blocks, so that's my rise, and that's equal to 2. And now, so what I can merely do, slope is equal to, and you can just use the symbol for slope, which remember is a lowercase m, rise over run. That's what our slope is. And so in this case, the rise was positive 2, and the run was positive 4. You get a fraction. Always reduce fractions, by the way, for your answers. So the slope of that line is 1/2. And just like we suspected, it's positive, as it should be, and not very steep. The slope is 1/2, less than 1. So that would be the slope of that line. Now, of course, you know other ways to calculate the slope as well. There's a slope formula that you probably recall using. So you will get the same result anyway. Call one of the points x1, y1, and call the other point x2, y2. Now it doesn't matter which point you call x1, y1, it'll work regardless of which point you pick. So my y2 is 3, my y1 is a 1, okay, x2 is 4 minus, and x1 is 0. Now work this out carefully. So you're going to end up with a 2, 4 minus 0 is 4, and look at that, by golly, we still get 1/2, don't we? So that's at least 2 different ways you know how to calculate the slope of a line. It's not all that difficult. And like I say, it's just a review of material that you did back in Math 1700. Now, what if you're looking at a line that intersects a curve in two places, in 2 points? That is what we call a secant line, S-E-C-A-N-T. Calculating a secant line that intersects a curve, calculating the slope of that secant line, is really no different than what we've just done. All right. So again, pick out 2 points. Here's 1 point there. In fact, I'm pretty sure this is the same line as in the previous example we just did. So if you call this point here 0, 1, and here's another point. Notice I'm picking points that are directly on grid marks, where grid marks cross, where grid lines cross. So that would be 4 and 3. And so now you can get the slope of that secant line relatively straightforward. And again, if you want to use your slope formula, it's exactly the same calculation we did just up above. x2 minus x1. And you plug your numbers in, blah, 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 blah. Like I say, it's the same numbers and everything. So you're just going to get 1 over 2. Now that's the slope of the secant line, but what if you wanted to get the equation of that secant line? What would you do in that case? Well, in this case, it's easy, because if you look carefully at your graph, if you want to put it in slope-intercept form, remember that looks like y equals mx plus b. That's called slope-intercept form. You could also use another form. There's 2-point form you could use as well. But all you need to do here is put in 1/2 for your m. M stands for your slope. B stands for your y-intercept. Now this one is fairly easy because I can see what the y-intercept is, right? I can clearly see that this line has a y-intercept of positive 1. So my equation here would just be y equals 1/2 x. 1/2 goes in front of your x. Don't forget your x. And plus 1. There's the equation of that secant line. And like I say, it's relatively straightforward technique. If you couldn't see the y-intercept, like we did here in this example, then all you would have to do is take the coordinates of any point on the line, plug it into your equation, after you've put in your slope, of course, and the b then is the only thing you don't know. Any point on the line is a solution to that line, you see? Secant is also called the average slope of the curve between the two x values. So remember that. Anytime you see a problem that asks for the average slope, well, that's asking for the slope of the secant line between those 2 points on the curve. On the top of page 19, here's another example. And this one again is pretty much the same as the one we just did. It says sketch and find the slope of the secant line. Well, I think they've already got it sketched there for us. Between x equals 1 and x equals 2. Well, there's x equals 1 on the x-axis. So this point right there is 1 point. And x equals 2, looks like it's a little bit off. Let's assume that they both go through that point right there. Okay? And they give us what the function is as well. Well, finding the equation of that secant line is, again, relatively straightforward. All right, it is relatively straightforward. I can see my x's and my y's. This point right here, for example, that's 2 and 0. That's what we call the x-intercept. And this point up here is actually at 1, 3. Okay? So again, if they want us to find the equation of that secant line now, step number 1 would be to calculate the slope. So we'll go y2 minus y1 over x2 minus x1. And that would become equal to, and I'll call this point down here x1, y1, and I'll call the point up there x2, y2. Putting those coordinates in beside those x's and y's, it kind of lessens the chance of making an error here. So I'm going to have y1 is, or y2 is 3, sorry, take away. y1 is 0. And let me see, x2 is 1, take away, and x1 is 2. Now I can see that this slope is going to be negative because it's sloping upward to the left. And it's fairly steep, so you're going to have bigger, it's going to be bigger than a half this time. So 3 take away 1 is 3. 1 take away 2, well, that's negative 1. And so now this, of course, you never leave a negative on the bottom, and 3 over 1 is just 3. So this slope is negative 3. That's what the slope of the line is. Now, how would you get the equation of it? Because you'll notice on this graph, you can't see what the actual y-intercept is, can you? All right, so what we do to get the equation, this is similar to what some types of problems we did in the conic sections. Let's write the equation with the slope in there. So that's going to be y equals negative 3x plus, and now I don't know what the y-intercept is, the b. So just take any point up here, any point that's on that secant line. Like you can plug in 2 and 0, or you can plug in 1 and 3. It doesn't matter. You'll get the same answer regardless of what you do. Let's suppose I decide to plug in, well, I'll plug in the 1 and the 3. Although the 2 and the 0 would work just as fine. So y is 3, negative 3, x is 1, plus b. Negative 3 times 1 is negative 3. You bring that to the other side, and you'll get a 6 is equal to b. There you go. That's your y-intercept. Even though I can't see it, that looks like a reasonable result. If I were to extend that line, yeah, it should hit the y-axis at 6. So now finally my equation is y equals negative 3x plus 6. And there is your equation of that secant line. Like I say, this is nothing new. You've been doing things like this previously anyway. Excuse me. The only difference is you probably haven't been finding equations by referring to them as secant lines. But remember, a secant line is just a line that intersects a curve in two places. All right. This example right here, I'll leave this one for you to try. Again, this is on page 19. Now, one thing you need to notice, you're given the two x values that they want to get the average slope. Look at that. That's your secant line. But do you notice that they don't tell you what the y values are? All right. So if you want to use your slope formula to get your slope, you need to get your y values. Well, the way you get your y values is easy enough. First of all, plug in x equals negative 2 into your equation, and you will get the y value corresponding to that x value. And secondly, you plug x equals 1 into that original equation, and you'll get the y value corresponding to x equals 1. And once you have your x's and your y's, getting the slope is easy, and finding the equation is also easy. And I'll also leave this example on the bottom of page 19 for you to try. Calculate the average slope, secant line, of the graph between x equals 2, right there. Now this one is actually fairly straightforward, I think, because you can actually see what the coordinates are, and x equals 4 right there. So there's your second point, and your secant line would look something like, something like that. I can't draw very well just using the stylus. So I'll leave that one for you to try as well. Okay? That was just a little bit of a review. Now, when it comes to calculus, though, like finding slopes of secant lines, well, that's nice. But in calculus, and not just in calculus, but in a lot of problems in mathematics, we want the slope of something called the tangent line. All right? That's what we're after. That's the goal of this lesson here. How do we get the slope, and in fact get the equation of a tangent line to a curve? Now, a tangent line does not intersect a curve in two places. A tangent line only intersects a curve in one place. You see that? Here's your definition. Graphically, the tangent line is the slope of the curve at one point only, and there's the point right there. It touches the curve at that point, only at that point, and it's perpendicular to the curve at that point. And it kind of means that, like, if you drew a line perpendicular to the tangent line, it would also be perpendicular to the curve as well. That perpendicular line, by the way, is called the normal line. And we'll be seeing that again in just a little while. Now, we've got a problem. We've got a problem, ladies and gentlemen. Look at that tangent line right there. Isn't that beautiful? Yes, sir. Lovely looking tangent line. Now, but what's the problem? How do you get the slope of that? How do you get the slope of that tangent line? I can see it looks positive because it's going off to the right. It's not very steep. Now, you might be able to look at your graph, for example, and pick out some points. Like here's a point. Let me get my marker. Here's a point that it looks like is right on grid marks. Here's a point that's right on grid marks. In fact, even this point here, which is called the point of tangency, that looks like it's directly where grids cross each other. So you can get the coordinates there. But in general, getting the slope and getting the equation of a tangent line is not trivial. It is not. That was a big problem in mathematics hundreds of years ago when I was just a boy. This little diagram here on the bottom of this page should clearly explain that if you've got a curve, everyone, depending on where the tangent line is located on that curve, your slope is going to be different, isn't it? And that's why if you ever asked, or if you ever wanted to find the slope of a curve, you have to very specifically say what is the x value, or what are the coordinates of the point where you're trying to find that slope. Here's a tangent line, for example, right there. Now, I might be able to find out some points on that line. I might be able to locate where they're crossing exactly where grids intersect, and maybe I could get the slope. But I'll tell you one thing, is going up to the right, so that slope is going to be positive something. Here is another tangent line to that same curve. This time, though, it's touching right, it looks like to be the vertex. If that was a parabola, that would be your vertex there. And now that's a horizontal line. The tangent line this time is horizontal, but notice it's only intersecting at one point. And we all know, I hope you know, that the slope of a horizontal line is 0. Okay? The slope of a vertical line, by the way, straight up and down, would be undefined. Now here's another one. Look, same curve, same exact curve, but now the tangent line is located at a different point, right there. And I notice that this line is sloping upward to the left, so whatever it is, if we could calculate it, it's negative something in this case. All right. So it's important to note, like I was just saying, that if you're after the slope of a curve, you really, 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 really do have to stress what is the coordinates. What are the coordinates of the point? Even if you just have the x value for some applications, you definitely need to determine, to specify where that tangent line is touching the curve too. All right. Algebraically, the tangent line is much more difficult to define, and it will be the focus of this unit. Like I was saying, this is a problem that mathematicians were having for years. Now, most of the students doing this course are either going in for engineering or with some kind of a science background. I can remember when I was doing science in high school, way, way, way a long time ago, doing things called heating curves and cooling curves, where you just basically take some water, perhaps boil it, and then record the temperature as it began to cool. And of course, you get a curve. And perhaps your teacher or your instructor asked you then to find out, like, what is the slope of that curve at a certain point? And that's what they're asking us to do here. Draw a tangent line and use it to calculate the slope of the curve at the required points. Well, here's the required points. One of them is at x equals 0. All right, well, where's x equals 0? Okay, well, there's x equals 0 right there. See that? Actually, the curve goes through the origin. So if you were to draw the tangent line, it would look something like, well, I don't know, something like this here. That's approximately what it would look like. Now, you could go ahead and estimate some points here and estimate some points up there, yes, and that would give you a fairly good approximation for the slope of that line. All right, that's what the tangent line looks like right there. And you'd probably come up with a fairly half-decent estimate anyway. What about at the other one, x equals 1? Okay, well, the tangent line right here, there's x equals 1. The tangent line, remember, now hits it in just one point, so it would look kind of something like this. All right, something like that anyway. Now, what's the slope of that line? Well, it's positive something. And again, you could really get a good estimate of what the slope of that line is by finding approximately a point up here somewhere and maybe a point down here somewhere, getting the coordinates, they may be decimals in this case, and then going ahead and using your slope formula and getting the slope that way. All right? Kind of a crude method though, isn't it? Kind of a crude method, but it works. And sometimes you have to use a method like that. Sometimes you have no choice. But we're going to be looking at a slightly different way. All right? So you can try that. Here's another example on page 21. And what they want you to do here is calculate the slope of the two lines in the graph below. Well, again, that's fairly easy. I'm going to leave that one for you to try as well. Really, all you need to do is locate points that are exactly on that line. Make sure you get them where the grid lines cross so that your coordinates are exactly correct. And I can see several good points that you could use for each of those lines, in fact. All right. So calculate the slope of the lines and then find the equation of each line. Again, that's not difficult. If you can see the y-intercepts, well, then you don't even really need to calculate the b. But if you want to calculate them, we'll just plug any point that's on that line, on either of the lines, into the appropriate equation. Okay? Now, so remember, our goal is to try to determine a way to come up with the slope of a tangent line to a curve. We want to be exact. That's one fault that mathematicians have. We want to come up with a technique that will allow us to accurately and exactly, if possible, come up with the slope of a tangent line. All right? And that's where the next lesson comes in. And I'm going to stop this video here because we're over 20 minutes in. So in the next video, I'm going to actually be looking at a tangent line. Here's a nice curve right there, a nice blue curve, although the color doesn't matter. What we're going to do, I'm going to show you a technique where if you want to find the slope of a tangent line, you can actually use a secant line, which remember now intersects a curve in 2 points, to approximate the slope of the tangent line. All right, so that's what I'll start in the next video. So I'll finish this here, and I'll see you again in just a moment. Bye-bye.